All right. Before the break, I said that there are different kinds of pinouts on the different interfaces. And the pinout depends on what equipment you're on, what device it is. Just to rehearse and see if you understood anything which we talked about previously. How many, in this little picture up here, how many broadcast domains is this? Broadcast domains. It's all one broadcast domain, right? How many collision domains are there? This one. There's stuff connected here. There's one up here, right? There's one here. This one is a single one. And there's 3 up here, down here, right? So 1, 2, 3, 4, 5, 6. All right? There's 6 different collision domains. There's 1 broadcast domain. Now, we talked about the hubs and repeaters previously. Now, I'm going to look at this collision domain here, because this is a really interesting collision domain. Because the interesting part of this collision domain is that it's only 2 interfaces. There's one on the PC network card and there's one on the switch network card. And that's the whole thing inside that collision domain, right? It's the only thing. That's the whole collision domain. Now, Ethernet, we said previously, is using this algorithm to decide whether I can send data or not. And it uses this on all collision domains. Now, this collision domain is a really small one. And if you look at this collision domain, the only thing is these 2, and there's a wire in between, a cable in between. Now that cable usually is a twisted pair, unshielded twisted pair. And it's 8 pins in that unshielded twisted pair cable. Out of those 8 pins, we're using 4. We're using 1 and 2 and 3 and 6. If you have an MDI pinout, which you do if you're a PC or a router, a PC and a router will transmit data on 1 and 2 and receive on 3 and 6. The most basic Ethernet, the most basic IP network, a datacom network you can create, is connecting 2 PCs together. Now, if I connect 2 PCs together, and they both have a pinout, MDI pinout, so they're transmitting on 1 and 2 and receiving on 3 and 6, if I connect these 2 using a straight-through cable, where pin number 1 goes to pin number 1 on the other side, pin 2 to 2, 3 to 3, 4 to 4, and all over. If I connect these 2 together, is it going to work? No, because they will both be sending on 1 and 2, and they're not going to hear anything because no one's going to send any data on 3 and 6, which is where I'm listening, where I'm receiving data. So in this kind of network, where I have the same pinout, I need to have a crossover cable. And a crossover cable is a cable where I send pin number 1 to pin 3, pin 2 to pin 6, both ways. So whatever one PC is sending on 1 and 2, the cable will switch it over and it will be received on the other side on 3 and 6. And the other PC sending on 1 and 2 will be switched over to 3 and 6, so I can receive whatever the other guy is sending. It's a crossover cable. Now, the other network equipments are using MDI crossover pinouts. And I'm using that if I'm a hub or a switch. Now, as you can probably guess, the crossover interfaces are doing the other thing. So we'll receive on 1 and 2, and I'll send on 3 and 6. So if you now look at this, we're a switch on one side and a PZ on the other side. The PZ is sending on 1 and 2, where the switch is receiving, and the switch is sending on 3 and 6, where the PC is receiving. So this then has to be a straight through cable. Okay? 1 to 1, 2 to 2, 3 to 3. So the basic rule is if I'm going within the group, so if I'm sending data from one equipment to another equipment and we have the same pinout, whether it's a PC to a router, a PC to a PC, hub to a switch to a switch, because they have the same pinout, we're going to use a cross cable. Because they have the same pinout, so the cable has to move the signal from one pin to another. Now, if I'm going between groups, so PC to switch, router to hub, router to switch, PC to hub, because they have different pinouts, I need a straight through cable. All right? The majority of switches today is auto-sensing in the sense that they're auto-sensing whether they can run half or full duplex, whether they can run 10 or 100 megabits. Most switches today are not auto-sensing as to what cable's in. There are switches coming to the market now, some of them. Most switches are not auto-sensing to this. There are switches that are auto-sensing to this, but most of them are not. There are even new switches that are not auto-sensing, and most of the switches in the network isn't really new ones. So, you okay with this? That's one thing of it. Now, the interesting part is what happens in this collision domain. This collision domain is a PC interface on one side, a switch interface on the other side. The PC is going to send his data on 1 and 2. The switch is going to send his data on 3 and 6. We have a straight through cable. Is there any possibility for a collision? Is it possible in this collision domain to have a collision? Not physical possible, all right? The PC is sending on 1 and 2. The switch is sending on 3 and 6. No way they can have a collision, right? Now, the algorithm says carrier sends. I'm supposed to listen to the line before I'm sending data. Now, if I'm the PC, I'm the only one sending on pin 1 and 2, right? So what am I supposed to listen for? If I'm not sending, is anyone else sending on pin 1 and 2? No. So do I need to listen before I send data? Is it actually multiple access on my 2 pins? No. And since we can't have collisions, do I need collision detection? No. I do. That's what I'm coming to. In this environment, in this connection, where I'm connecting PC to switch, I don't need this. I don't need collision detection. I don't need it. I'll turn it off. I don't listen before I send. I can't have collisions, meaning that in this case, I can send and receive data at the same time, because it's not going to be a collision. I cannot do this here, because this is a big collision domain. There's lots of users on there, and there's a hub. And because there's a hub, the hub will receive whatever and send it to everyone. So in this case, in the collision domain, this big, I'll need this. In this case, the collision domain is so small, I don't need it. So we'll turn it off, and that's what we call full duplex. We'll send data both ways at the same time. And we can do it because of the size of the collision domain. We'll just turn it off. We don't need it. And this is what we do with Ethernet today. Almost all users everywhere in all companies is on a switch port, and they're running 100 megabits at least. And then we don't need collision detection. We don't need this contention-based stuff. We can send and receive data at the same time. How much more efficient is that? Lots. I mean, the easy part is to say, instead of just sending 10 megabits one way and have to wait for 10 megabits the other way, I can send 10 megabits both ways. So at least double. But it's even more than that, because you're not going to have any collisions. So any retransmission you have to do here, you're not going to have to do that because you're not going to have any collisions. So it's more than double the efficiency.
These need to come from the sensor training because you don't know, you don't change that whatever you connect.
Yes, and that's the thing. What you need is you need a network card and you need a switch that understands full duplex. Now, if you have a network card today, you bought it within the last 4 or 5 years, it is auto sensing. It will sense whether it's connected to a switch or whether it's connected to a hub. And if it's connected to a hub, it will say, okay, hub, I'll go half duplex. If I'm connected to a switch, say, okay, this is a switch, and we're auto sense that there's a switch, and we'll auto sense the speed, and we'll also auto sense the duplex. Now, if you go back 5, 6 years ago, this auto sense standard isn't. When they wrote the standard, they wrote it too loose. There were different implementations from the ones doing the ships doing the auto sensing. So you can still have that, not as much today as you had 5, 10 years ago. But you have to make sure that, as you were talking about, you have to make sure that both sides understand this and that it works. One of the worst things that could happen to you is if you connect something to the switch, for instance, a server, and the server thinks that it is half duplex, and the switch thinks that it is full duplex. So you have a duplex mismatch. And that could happen with AutoSense. It used to happen a lot 5, 10 years ago. Doesn't happen as much today. But if you have a mismatch, what's going to happen? Well, as long as there's no load on the server, chances are you're going to just be sending data one way at a time. And as long as you're sending data one way at a time, it's not going to be a problem. But when the load to the server increases, the switch is going to start sending data at the same time as he receives data, because he thinks it's full duplex. And if it's full duplex, it's okay to send and receive data at the same time. Now, if the server thinks it's half duplex, and he's receiving and sending data at the same time, he's going to say, well, this is half duplex, and if I'm receiving and sending at the same time, that's a collision. And he'll throw it away. Which means you're going to have retransmission, which is going to get even more load on here, which means you're going to have even less transmissions getting through because you're going to have even more collisions. Or the switch is going to, the server is going to think that there is more collisions.
How many parameters, so to say, belongs to this kind of not collision and collision? What kind of, is it the switch itself or the cable? Or
I don't understand. I don't understand.
No collisions nowadays,
Yeah.
before.
Yeah. But the thing is, for this to work, it has to be switched to PC, and the PC and the switch has to be able to run full duplex. They also have to be configured or auto-sense that they can run full duplex. If they can, or if they're configured to run full duplex, no problem. But if you have an auto-sense problem, or if someone messes up the configuration and actually goes in and tells the switch, this is full duplex, and he says the service, this is half duplex, then you're going to have a problem. Still today, yeah. And the recommendation today is still, when we do this, these courses, we still recommend people, network administrators, to manually put these to full duplex. Between switches and switches and switches and routers and servers and stuff. And leave out the sense on towards the users. Because the users, if they have a mismatch, it's not a big deal. It's going to affect one user, and he's going to scream if he notices. Now, if it affects between the switches or between switches and servers, it's going to affect lots of people. So still today, we recommend that you configure it. You configure it. You don't leave it up to AutoSense, even though AutoSense today is much, much better than it used to be.
In our PCs we probably have also cells.
Yes. Yes.
In our offices, we have probably one cable from each and every PC to a switch.
Yeah. Yes. But they're all in the walls. Lots of cables, yeah. Obviously, if these all users all are on 100 megabit links, and they're full duplex 100 megabit links, that means this can't be 100 megabits. It might be gigabit or something. And the server, if it got loads of people connected to it, if that's on a 100 megabit link and all uses 300 of them, is also on 100 megabits, well, there won't be any collision, but there will be buffering and too much traffic on the switch, and he will have to throw things away because he can't handle it. So you need to take that into account when you do the design of the network, right? Okay?
In order to have these real-time applications like voice over IP, do you need a full duplex network all the way from end to end?
Yes. Simple answer, yes. It's not a problem. You don't have to. It all depends on the traffic load, obviously. But today, this is not the problem, because how many hubs do you have? Not very much. Not very many. Promise.
So just as a question then, if you have a wireless access point, then the air interface is the equivalent of a cable, but it's also a collision domain, correct?
It's a collision domain, yeah.
Okay, so if I have 3 or 4 PCs connected to the wireless access point, then
They're sharing.
yeah, they're sharing the bandwidth and the
Yep.
collision detection happens. But if I've
Yep.
also got a switch built in, then something where I want lots of bandwidth, I should not connect it over the air. I should connect it,
Yeah.
for instance,
Yeah.
as
Wired.
network access.
Yeah. That's the problem with wireless, isn't it? Because wireless is, for me, wireless is very, very good because it allows me to not have any wires. But it's also a step backwards because we're not having this full duplex media anymore. We're using shared media. And shared media, sorry, for me that's a step backwards. If you're running office applications, Office, Word, or file sharing, or stuff like that, fine. But if you want to run real-time voice application or videos applications, wireless is not very good because it's shared media, right? You need to be able to make sure that you got the quality of service there, and if you're sharing media, whether it's half duplex or if you're sharing it over there, it's still sharing the media. You can still have, now you don't have collision detection in wireless, it's called collision avoidance. But it's the same thing. You can't be sure that you can send data. So short answer, yes. But I mean, what they've done all the years up to now in LANs to have quality of service is over-dimension. If you got 100 megabit links or gigabit links everywhere, and you're using 2% of it, do you need quality of service? Well, you got quality of service because you're not going to be able to get the switches or links to overload and you don't have any problem. But when you get extra amounts of data, then you need some quality of service to decide which goes and which waits. And that's going to be the problem with collision and collision domains, whether it's half duplex or if it's wireless.
What will happen in the future? We are not allowed to have security for duplex.
Sorry, in the future.
The wireless not will never have a security for duplex.
Full duplex, not any technology that I know of can run full duplex, but I'm not a wireless expert. So, but over there, so far as I know, with the standards we have so far, there's no full duplex, which means that anything over wireless you could have problems with. So straight through, 1-to-1, 1-to-1, 2-to-2, so on. straight through cable, straight through, crossover 1 to 3, 2 to 6, both ways. Which means that if you're connected to a hub, because the hub doesn't know and doesn't care about any transmissions, one at a time, we need to use the CSMICD algorithm to decide whether or not to send. If you're connected to the switch and the PC network card both understands and uses full duplex, we can then turn on full duplex, we can send and receive at the same time, having more aggregate traffic going through. This is the transceiver I talked about previously, the AUI attached, or whatever, fell out. Or whatever. With the AUI, you can have different transceivers, giving you options to connect different kinds of media to, for instance, this router. Not used today. If you're running Ethernet, it's UTP cable or it's fiber, so the router or switch is going to have that. But previously, when we were running 10 base T using twisted pair and 10 base 2 and 10 base 5, we had different media, so we needed different ways, different transceivers to connect it to the devices. This is kind of fun. This is actually Synoptics 5000 chassis. It's kind of funny for me because this was the first equipment I did training on. First instructor certification I had was on this 5000 chassis. Basically what it's here for is a big hub. It started out as a big concentrator or a hub. Nortel or Bay Networks, as the Synoptics were previously known. Synoptics was created by Bay, and then Bay was bought up by Nortel. This is basically, or were, a big hub. There were lots of those chassis sold. And they're more or less useless today. The hub functionality, we talked about that. We receive and send on the TP, and there's one at a time because we're shared media. Now the switches, as we previously said, creates different collision domains, separating the collision domains into smaller ones, and connect the broadcast domains. One broadcast domain, multiple collision domains. The switch understands the Ethernet frame. So when I'm sending an Ethernet frame, in the Ethernet frame, as we talked about previously, there's a destination address and there's a source address. What the switch will do, any frame coming into a switch, the first thing the switch will look at is the source MAC address. Where is it coming from? And by looking at the source MAC address, the switch will save in something called, in this case, a switch lookup table. CISO calls it a content addressable memory, CAM. Nortel calls it a forwarding table. In that memory area, I will write up all MAC addresses I've seen and the ports I received them on. So as soon as someone sends data to the switch is going to look at the source MAC address, and the switch will be, by doing that, when A sends something, it will go to the hub will send it to everyone, and it will arrive at the switch on port 2. When the frame arrives at switch on port number 2, the switch is going to look at the source MAC address, A's MAC address, and it will go to his table and he will write A's MAC address, I've seen that, it arrived on port number 2. If C sends something, it will go to the hub will send it to B, it will throw it away unless it's for him. It will go to the switch, it will arrive on the switch on port number 3. When it arrives, the switch will go to his table and he will put C as having arrived, coming from port number 3. By doing this, the switch will look at the source MAC addresses, it will write it up in his table, and we will find out where all MAC addresses are. Once I've received the frame and I've looked at the source MAC address, I've updated my table, I will then go and look at the destination MAC address. I will get the destination MAC address, I will compare it to whatever I have in my switch lookup table, and if I have the destination MAC address in here, I know where to send it. And I will send it out on that port, and on that port only. So if A sends something, and I want it to go to this server, A is going to create an Ethernet frame. It will send it to the hub being level 1, is going to send it to the switch to everyone. Arrives at the switch, it will make sure that A is still on port number 2, and it will then look at the destination MAC address being the service MAC address. I will go into the table and I find that I've seen the server. It arrived on port number 6. So I will take A's frame and I will switch it out on port 6 only, because it's only that MAC address that's supposed to have it. And that's the difference between the hub and the switch. The hub does not understand the Ethernet frame. For a hub, a frame is a number of ones and zeros, lots of bits coming in. The hub has no clue what these ones and zeros stand for. It's just a signal. Lots of ones and zeros. Layer 1. The switch can take those ones and zeros, and he understands that the 48 first bits is the destination MAC address, so I can go get that. And we'll look at the next 48 bits, and he knows that those 48 bits is a source MAC address. And I will write that up in my switch lookup table. And by looking at the frames coming in, I can decide where things are connected, and I can therefore also decide where I need to send stuff. Yeah. Remember previously we talked about bridges, right? And I said bridges are 2 ports, switches are multi-port, right? Now, it's not as simple as that. Basically, the difference between a switch and a bridge is that the bridge has 2 ports, fewer ports. It's doing the lookup thing in software, and it's not very quick. It only has 10 megabits media, usually, because it's old. Now, the switch is doing the same thing as the bridge. It's the difference between an Amazon or a V70. They're both cars, Volvo cars. Now, there's a big difference. You can ride it on the roads. It's the same thing with bridges. Bridges and switches are doing the same thing. The switch has loads of ports. There's switches with hundreds of ports on them. They have support for different kinds of media, not only 10 megabits, but 100 megabits, gigabits, and maybe 10 gigabit Ethernet. But the major difference is in the actual forwarding, because the switch is doing this in hardware. There is application-specific integrated circuits, ASICs, that is doing this in switches. So a switch today can do this wire speed. So that's the major difference. That's actually the big difference between the bridge and the switch. And so they're doing the same thing, but the switch is doing it much, much quicker because it's doing it in hardware. So a switch today, you don't have to upgrade it. If you have a bridge, replace it. You might find hubs on your network here in Ericsson and Kista. I don't know because I haven't been there looking at your equipment. You will not find bridges. I promise. If you do, give me a call because I want to see it. Bridges and switches doing the same thing. They're all switches today.
Is this table updated dynamically?
Yeah.
So if
Yeah.
you plug your PC from
Yeah.
one port and put it on another, then it will...
Yeah. It updates automatically. Yeah. As soon as I start sending something, if I would move A, for instance, from port 2 to port 8, say, as soon as A sends something, it will send the frame, and the switch will remove him from port 2 and put him to port 8. And you don't have to do anything about it. If it's not sending anything, it might be a couple of seconds perhaps before but the higher level protocols is going to take care of that, so as a user you don't have to care. If it times out, for instance, we're going to broadcast, and once we broadcast it, A is going to have that broadcast, and once you get the broadcast, he'll send an answer, and once I've sent the answer, back in the switch lookup table again. So it's not a problem. It's dynamic. There's one thing more that you should know about the switch lookup table. Now that switch lookup table is obviously in RAM, in RAM memory, in memory. Now that memory space isn't unlimited, unfortunately. So if you have a switch that has been running in a closet for 2 or 3 years, if I wouldn't do anything with the switch lookup table, it will be sooner or later getting full. There's consultants coming in and going. You're switching network cards on your service. You're switching network cards on your PC. You're switching your PC to a new one, and you're going to create new MAC addresses. Now, if we never emptied the switch lookup table, it would get full sooner or later. So there's a timer on the lookup table. Usually, most switches is 5 minutes. So if you haven't sent any data for 5 minutes, you're going to be removed from the switch lookup table. And when the switch receives something that he doesn't know where to send, he will do something called a flood. And the flood is basically sending it out on all ports. So if A is sending something to D, and D hasn't sent any data at all to the switch for 5 minutes, switch won't know where D is, and when it arrives at the switch, he will check his lookup table. If D's MAC address isn't in there, out on all ports. So in that case, I will temporarily work the same way as the hub do. As soon as D gets it, one of the good things with Datacom, if I send something to D, D is going to look at it and I'm going to send something back, right? So as soon as D sends something back in the switch lookup table, and then we don't have to flood anymore. So but temporarily, I might need to do some flooding. All right? Questions on switches? You okay?
So a PC doesn't periodically
No.
send out a little
No. But if you're, for instance, is running Windows with uplink, never mind if you have any application running. If you're running Windows, you will create data every 5 minutes at least, unless you have some filtering extra on. Because a PC run-in, if you haven't created any data in 5 minutes on the PC, you're dead. You'll shut down. So even if you're not working. There's a difference between routers and routers, obviously. But they all do the same thing. The routers is responsible for keeping track of the networks. It's the routers that allow me to go from my network, from my LAN, to another one. And the routers is really important to us because it's the routers that keep track of the IP networks. So we'll talk much, much more about routers later on. Obviously, because the router is routing on layer 3, IP layer, and routing IP packets, but there could be different access media. You can have Ethernet on one network, you can have token ring on one, you can have WAN links with PPP or whatever on. So you could have different interfaces on the routers, obviously. Questions? I think you got some extra slides in the book, but you can look through those on your own. Before we have lunch, we'll go through VLANs, and I'm also going to talk, most of it we already talked about, WLANs, or wireless LANs. VLANs is a virtual LAN. We use VLANs to segment, do segmentation, split users from each other. There's lots of different reasons to do it. If you have applications running lots of broadcasts, for instance, lots of broadcasts, if I'm not interested in no broadcast, I don't want to be receiving them. If you got lots of users on a LAN, obviously there's going to be more broadcast traffic going. So we want to do segmentation to release the number or lessen the number of broadcasts on the network. We also have different other reasons to do VLANs. We're going to do segmentation for security reason. It's usually not a good idea to have the Ethernet connection in the library or the public places in Ericsson. They probably shouldn't be connected to the same place as your most secret research guys are. Probably want those to be on different networks. I used to work in a school, or I did a PC Convux kurs, and we did that on a gymnasium, and we were responsible for the PCs. Now, if you ever been to a school and watched or looked at their data rooms or data rooms or classrooms, you realize that you don't want your students to be on the same network, be on the same LAN as the ones that put the teachers and the ones putting the grades out for the students and stuff. We want those separated. You wouldn't believe the amount of garbage that showed up in the classrooms, in the data classrooms. So we want to separate people. You also want to separate people because if there is a failure somewhere, we don't want everyone in the whole company to suffer from that failure. We want to have smaller failure domains so it doesn't affect as many people, and it's also easier to find the cause of that failure and therefore to fix it. So lots of reasons to have VLANs to split up, do segmentation. So what's a VLAN then? Well, a VLAN, I used to do a little history thing. How many broadcast domains is this if I don't connect them? How many broadcast domains? 2. If I connect them with a crossover cable here, how many broadcast domains are there? 1. If I want them to stay different broadcast domains, different local area networks, but I still want to have traffic go between them, what do I need? A router. So I'll add a router up here. And I connect this switch to it, and I connect that switch to it. Now these are 2 broadcast domains. I can send data from this LAN to the router, and the router will route it and send it out on this one. They're 2 different broadcast domains, right? Now this is the way it used to be 15 years back. Because routers traditionally are more expensive than switches, and also traditionally old routers did their forwarding in software, we didn't want to have lots of routers because they were expensive and they were slow. So what we used to do is create large broadcast domains with lots of switches, lots of users, and then we routed where we had to. That's the way it used to be. Now, some year later, along came a new switch. Now, the thing with this switch is it's a VLAN capable switch. Now, a VLAN capable switch is a switch where I can, on one single switch, have more than one broadcast domain. In this case, I've created 3 different virtual LANs, all on the same switch. It's still a switch. It's not one broadcast domain. There are 3 broadcast domains on the same device. Now, if I want to send data from here to here, it's fine. If I want to send data from here to here, can I do that with a switch? If I want to go from one broadcast domain to another broadcast domain, what do I need? A router. So we needed to add a router to this. So a VLAN is a separate broadcast domain. So So the definition of a VLAN is a broadcast domain. It's the same as the LAN, right? There is no difference actually between a LAN and a VLAN. It's just the implementation. It's just the equipment it's running on. It's called a VLAN because it's a virtual LAN within a device. It could have multiple VLANs, whereas the ordinary old switch only had a single broadcast domain, one single LAN. Now what we did to begin with was we connected the router to the switch, and we had one cable for every single LAN, VLAN. So I'm going to add a green one and a red one, and then we routed between the broadcast domains, same as we did previously. I'll send it from one VLAN to the switch. I'll add a green one to send it back on the green VLAN. Now that's okay if I got 3 VLANs. If I got 50 VLANs on this switch, and I want to route between them, I need 50 cables to go to the routers, and the router would need 50 interfaces. That's going to be one expensive router, and if this is a desktop switch, it's not going to be 50 ports on it. So to be able to do this, we came up with something called a trunking protocol. And all users or all manufacturers of switches had their own trunking protocol. Cisco is the one that has kept on to their own trunking protocol longest. Today, every single one is using a trunking protocol 802.1q. Usually a big Q, but never mind. As you can see, it's an IEEE standard for trunking traffic. What the trunk is for is sending traffic from different VLANs over the same link. We'll get back to this in a minute. So in this case, I can send traffic from the black VLAN from my PC here. I can send it to the switch. The switch will send it to the router. When I'm sending it over here, the trunking protocol is going to add some extra information to let the router know that this is coming from the black VLAN. It goes to the router receives it, and as every other time when we route a frame, we remove the frame. We look into the IP packet, and the router sees that this IP packet needs to go back out to the red VLAN. So we'll add a new frame, same as always, new frame, and I'll add a red tag to it, red information. I'll send it to this on the same link back to the switch, and when the switch receives it, it will see that the frame is tagged belonging to the red VLAN, and I'll send it out to the red VLAN. So now I'm going from one broadcast domain to the router and back out to the other broadcast domain, same as we did previously. Only difference is, instead of having separate switches and a separate router, we have a VLAN switch, a trunk, and a router. This used to be called, or is called, router on a stick. Wait. This is a router, and that's the stick. Now, that works as well, but what we have later, someone said, well, that's good and fine, but why would we have a single switch and a separate router? Why don't we move the router functionality into the switch? Why do we have separate routers and separate switches? So what they did is they took the router functionality and they moved it into the switch. This is what we call a router switch, or a layer 3 switch, or a multi-layer switch. It's a switch because I can still switch within the VLAN. I can go from here to here. It's a switching decision. It's one Ethernet frame to another thing with Ethernet. But I can also go from here to here, but I need to go via the router functionality. Now it's built into the device. Now, we used to call them router switches, and then the marketing people came along and said, well, router switches isn't any good. Let's call them layer 3 switches. because they can both switch and route. So they can route between VLANs and they can switch within the VLAN. Now obviously, I can connect this one to the multi-layer switch using a trunk, 821Q. It's the same VLAN here as here. It's the same black VLAN here as here. So VLAN is used for separating people, separating segmentation. Now these are really quick ones today, because today the multi-layer switches you buy today is also doing the routing thing in hardware. So nowadays it doesn't really matter whether you route or switch, because the router switch or the multi-layer switch is routing as quick as it's switching. So now we don't want to have large broadcast domains with lots of switching and route because we have to, because the router is slow. We want to have small broadcast domain, lots of VLANs, and we route because we want to. Another thing with this is because we're doing a routing decision here, instead of doing as a switching decision, we'll take this up to layer 3, which means that we can implement firewalls and filters on the IP level. So we look at IP addresses. I might, for instance, say, you're not allowed, if you're on this VLAN having this IP address, you're not allowed to go to that VLAN. I can stop that by filtering or having a firewall functionality. So I can create smaller parts so I can be more secure.
So why do people still make the layers with switches?
Because they're cheap. But the layer 2 switches you buy, if you buy an enterprise layer 2 switch today, it's going to be VLAN capable. Every single switch you buy from Cisco or Nortel or 3Com or whatever, if it's enterprise grade, it's VLAN capable. This kind of switch with only one broadcast domain on, that's for home users today. And even some of the broadband routers you buy with built-in switches, even some of those have capability for VLANs today. So an ordinary layer 2 switch without VLANs, you don't buy that. A VLAN-capable switch is still much cheaper than the multi-layer switch. There are networks that only have multi-layer switches. Aftonposten in Oslo. They've created a new network some years ago. They've thrown out all switches. Every single user's everything is connected directly to a multi-layer switch.
So they need more administration stuff.
Depends, yeah, but obviously, but it's also simpler. Or not simpler, but it's more efficient anyway. And it's not really that complicated to do the configuration either. Whereas many companies have a few of those, a number of them in the core or distribution layers, and have access layers, we'll talk about that later, with layer 2 switches, VLAN-capable switches, to get a lot of ports for a less amount of money, because we're back with the budget constraints we talked about earlier.
How big can these layer 3 switches be? How many ports can you have? How many?
Lots of hundreds. I'm doing some. I'm doing Nortel training. Nortel has a 8600 switch platform. It's 10 slots, and I think you can reach 384 ports in the chassis. Unless they've created some new modules now, but so hundreds of them anyway. And if you want to, you can route on every single port, or you can switch on them. You decide, and it doesn't affect the performance. You route as quick as they switch, which is why these are really nice.
What's the routing protocol that's typically used?
Typically today OSPF, but it could be RIP, it could be some other thing. But if I need to mention one routing protocol, the biggest routing protocol is OSPF. Biggest is as in most used. Yeah. But these can these can route RIP and other routing protocols, BGPs and whatever as well. Depends on the manufacturer and the module, obviously. So this is basically the same thing as I went through with you. VLAN operations. We create within the switch different VLANs, virtual LANs, different broadcast domains. If we want to connect them, we do that with a trunk. We run a trunking protocol. Today, the trunking protocol 802.1q. It's a standard. And we use the trunk to carry traffic from multiple VLANs. To make sure that the other side knows what VLAN the frame is connected to, we put an extra information on there. Which means that I can trunk traffic if I'm connected. This is from a switch Cisco course, as you can see. If I'm connected on VLAN number 1, I can send VLAN number 1 to my switch. I will trunk it up to another switch. I can trunk it down to another switch and take it out. Same VLAN somewhere else. Same broadcast domain. I can do the same with VLAN 2 and VLAN 3, obviously. Don't know how important this is for you, but when we send data using 802.1q, we put an extra frame, an extra 4 bytes in the frame. That frame is telling the receiving end what VLAN it belongs to. Now, there is a possibility in the standard to have something that Cisco called native VLAN. It's an untagged VLAN. One single VLAN. So imagine you have 20 VLANs on this side, and you have the same 20 VLANs on this side. It is possible to send all 20 over this trunk using 801.1q. If you want to, and some manufacturers, Cisco for instance, is using one of the VLAN as a native VLAN. Basically saying the native VLAN doesn't contain the tag. There's nothing in the frame that tells the receiving side what VLAN I belong to. So if I got 20 VLANs on this side, 19 of them is going to contain a tag when I'm sending them over here. The 20th, the untagged one, the native one, is not going to contain a tag. Now, because it's just one, when I receive an untagged frame here, what VLAN does it belong to? Well, the native one. If I receive anything else, it has a tag. And if it has a tag, the tag will tell me what VLAN it belongs to. Now, this is important because some manufacturers have not implemented the untagged one, the untagged VLAN. For instance, I did Nortel training before I did Cisco training. And in Nortel, we never ever discussed this untagged, or we didn't anyway in my classes, before I went to a Cisco course. And the Cisco instructor said, oh, by the way, there's a native VLAN on here. I said, what? So you need to be aware of it. Now, the use for the native VLAN, that can be debated. Because, to be honest with you, I don't really know a reason for it, except for something that showed up much, much later, has to do with IP phones. Cisco trying to say that, well, never mind. You should, we don't go into it. Native VLAN, untagged, one untagged VLAN. You might have it on some manufacturers don't have it. So you need to be able to know that so you know how to handle it, if it is there. At the top is the ordinary Ethernet frame, destination address, source address, length or type field, the data, and the checksum. When we add the frame, when we send the frame over the trunk, so we add the extra information, what we'll do is we'll put in 4 extra bytes after the source MAC address. That's the tag, 4 extra bytes of data. And the tag belongs of, it has 2 bytes which is a new type field. If you look at the position of this type field in the tag, notice that this type field, those 2 bytes here, they're going to be at the same place as the type field used to be, right, in the ordinary frame. So if a switch goes in, he looks at the type field, and where he's supposed to see 0800 because it's an IP packet, instead of that he sees 8100. The switch knows that this is a tagged frame. And that's the use of this. It's to let the switch know that this is a tagged frame. 2 bytes. Then there's 3 bytes used for priority. This is part of the IEEE 802.1p priority bits. These 3 bits allow me, for quality of service reason, to prioritize in 8 different levels, 0 to 7, 3 bits, between traffic. So it's a possibility to prioritize on layer 2. Because this is an IEEE standard, there's a bit in here for token ring purposes. It will tell me, it's called a canonical forward indicator, or canonical forward ID. It tells me whether it's token ring encapsulation or Ethernet encapsulation, so boring bit. Left is 12 bits, because we're not running token ring, right? That's why it's boring. Left is 12 bits. This is the 12 bits that lets the switch know which VLAN I'm part of. So I can be part of 1, I'll put 1 in here. If it's VLAN number 10, I'll put 10 here. 12 bits, max number is 4095. Now, you don't usually use 0, and you don't usually use 4095. So queue tagging usually is set to support 4094 VLANs. That's the maximum number you can have of VLANs in the tag. Obviously, if we add a tag in the middle of the frame, we need to redo the checksum at the end. So that's going to be done. This is also done in hardware, so it doesn't affect the switch. Questions? Anyone hungry? Right. Let's have an hour lunch then. We'll start 1:15.